Welcome to the Explainer. You know, we see smart machines literally everywhere these days. But how often do we actually stop to ask, how do they think? I mean, how do they take our incredibly messy, unpredictable world, cram it into their circuits, and then actually make reliable decisions? Well, our goal today is to completely demystify that entire process. We're going to take a fascinating journey under the hood of artificial intelligence, moving from the real-world robots you'd recognize on the street all the way down to the foundational computer science philosophy that actually makes them tick. Okay, let's dive right into this. We've got a really clear roadmap to guide us today. First, we'll meet the intelligent agents. Then, we'll explore the universal agent loop, see exactly how they translate messy reality, dig into the architecture of representation, and finally, look at time, logic, and action. Let's get started. Section 1. Meet the intelligent agents. To kick things off, let's step away from the abstract for a second and ground this in some tangible, real-world examples. Think about these four completely different archetypes of intelligent agents. Over on the far left, you've got an autonomous delivery robot. Its domain is purely physical, right? It's navigating hallways using cameras and lasers just to bring you a cup of coffee. But then, contrast that with the trading agent. That one lives entirely in the digital domain, rapidly interacting with financial markets to buy and sell. Or what about the intelligent tutoring system on the far right? That one is actually adapting to human behavior and cognitive learning. So the environments are radically different. But here is where it gets absolutely fascinating. Notice how, despite operating in these vastly different domains, every single intelligent agent is built on the exact same 5 foundational inputs. It doesn't matter if it's a delivery robot or a math tutor, it needs abilities, meaning what can it physically or digitally do? It needs prior knowledge, like a map of a building or the actual subject material it's teaching. It relies on past experience, it's driven by very specific goals, and finally, it reacts to observations, whether that's incoming laser sensor data or just a student's test score. This right here, this is the universal recipe for agency. Section 2. The universal agent loop. So now we know the ingredients they take in, but we really need to understand the common denominator of how they process all of that information. And this brilliantly illustrates the heartbeat of AI. It's this continuous cycle. Notice how the whole thing flows. The agent builds a model of its environment. Then, through perception, it figures out what the world is currently like based on new observations. From there, it decides what action it needs to take to achieve its goals. And finally, it learns. It updates its internal models based on the results of what just happened. This loop is so powerful because, if you think about it, it mirrors exactly how we humans instinctively learn and act in our own everyday lives. Section 3. Translating messy reality. Now, how do we turn all of that chaos into code? Here we run straight into the core conflict of this explainer, and honestly, the core conflict of computer science itself. The real world is just incredibly chaotic and ambiguous. But computers, they require absolute mathematical order. Which really begs the question, how does a machine actually bridge that gap? How does it translate our messy, totally unpredictable physical environment into formal logic that a silicon processor can actually crunch? Well, the answer is this translation pipeline. See, a computer simply cannot act on ambiguity. It has to take an informal, messy problem, like that scribble of chaotic lines on the left, and interpret it. It uses common sense reasoning to formalize the physical world into concrete specifications. And it's only once the problem is locked into that rigid, grid-like logic that the computer can actually process it and spit out a clear, actionable solution. Now, for that translation pipeline to actually work, the agent desperately needs a perfect representation of the world. And the anatomy of an ideal representation rests on 4 distinct pillars. First, it has to be expressive enough to hold all the necessary knowledge. Second, it must be natural, meaning it's compact and actually aligns with the problem at hand. Third, it has to be computable. This is huge. It allows the system to trade off just a little bit of perfect accuracy to get the processing speed it needs to survive. And finally, it must be acquirable, meaning the machine can actually reliably learn it from data or experience. Now, what's really interesting about this is seeing it in action. Let's bring back our diagnostic assistant from earlier and watch how it translates a problem. On the left, you've got this physical schematic. Wires, circuit breakers, lights, the whole shebang. But the computer doesn't see a room full of wires. It translates that physical reality into the logical fault tree you see on the right. If lights 1 and 2 go dark, it traces those logical branches backward. It asks, could it be circuit breaker 1? Could it be a wire fault? It is literally mapping physical reality into pure searchable logic. And what you just saw happening on that fault tree is called causal reasoning. Basically, it's the core task of searching through a massive space of possible problems to derive the actual causes for those symptoms. The agent is actively ruling out alternatives step by step. And crucially, because the logic is mathematically mapped out, it can actually explain its reasoning back to a human operator. Section 4. The architecture of representation. Okay, we are now going to peel back the deepest layer of the onion. Let's look at the heavy computer science theory that's powering this entire system. This brings us to a massive, almost philosophical concept in AI, the physical symbol system hypothesis. Now, a symbol is simply a meaningful physical pattern that can be manipulated. And the core hypothesis here states that a physical symbol system has the necessary and sufficient means for general intelligent action. In plain English, if a system can create, copy, modify, and destroy symbols, it already possesses the fundamental architecture required to be intelligent. But as you can imagine, managing all those symbols requires layers. Think of it kind of like an engine turning fuel into forward momentum. We have to start at the absolute bottom. Level 1 is just raw physical electricity, currents and voltages. That gets abstracted into level 2, digital circuits of ones and zeros. That gets grouped into assembly language, which then builds up to programming languages like C++ or Java, which finally allows for a high-level specification, giving us, at level 6, our problem solution. You literally can't solve a complex problem if you're just thinking about raw electricity. You absolutely need this hierarchy of representation. And navigating all those levels of abstraction, it's a really delicate balancing act for the agent. See, low-level descriptions like the granular wireframe on the right are vastly more accurate and predictive, but they are incredibly difficult to reason with at scale because there's just an immense amount of specific data. High-level descriptions, like the topographical map on the left, completely abstract away all those operational details. That makes it way easier to specify and solve the immediate problem without getting hopelessly bogged down by the raw data. Section 5, Time, Logic, and Action. And that brings us to our final section, and honestly, the ultimate inescapable practical constraint that every single intelligent system faces, the relentless ticking clock. We call this the chronology of reasoning. Just look at the massive gap in how time is spent here. Phase 1 is design time, which is carried out slowly and carefully by human engineers. Phase 2 is offline computation, where the agent crunches tons of data and compiles background knowledge before it is ever even active. But Phase 3, online computation, happens in the blink of an eye. This is the ultra-fast, real-time reasoning executed in that tiny, tiny gap between receiving a new piece of information and having to take immediate action. Because of that ticking clock in real time, machines use a brilliant concept called satisficing. So the crucial point here is that demanding absolute perfection can actually ruin a decision if it takes too long to calculate. Satisficing is the art of finding a solution that is simply good enough to be adequate, based purely on the specific constraints of the situation. If you look at the solution quality spectrum, you've got optimal on the far left. That's the theoretical, absolute best answer. But an agent constantly has to define what adequate actually means for its current task. Sometimes, sure, it can aim for approximately optimal. But very often, it lands on satisficing. And sometimes, in a total time crunch, it just has to go with probable, meaning it's merely likely to be a solution based on whatever data is available right now. Good decisions can for sure have bad outcomes, but paralysis by analysis is always a failure. This reality builds perfectly into the value of information over time. Plotting this out provides the ultimate visual proof of why agents absolutely must satisfice. That green line, that shows the quality of the solution improving as the machine thinks. But the red line is the time discount. That's how useful the action actually is in reality. Think about it. If an autonomous car waits to calculate the mathematically optimal steering angle to avoid a crash, the red line hits 0. The information becomes completely unactionable. You have to hit that ideal action window. Which leaves us with this final, truly fascinating question to ponder. If a machine has to intentionally sacrifice mathematical perfection just to be able to act in time, does true intelligence actually lie in raw processing logic? Or does it lie in knowing exactly when to stop thinking and start doing? Think about that the next time you see a delivery robot weaving around you on the sidewalk. Thanks for joining me on this explainer. I hope you walk away seeing our digital world just a little bit differently today.